looks like we're live. Hello everyone and welcome to yet another recreational programming session. Let's make a little bit of an announcement and officially start the stream. So we're gonna do a red circle live on Twitch. And what are we doing today on Twitch, a television website? Today we're trying to answer a question, do we need garbage collector anymore? Right, so that's a very interesting question. Not really that, right, but essentially today we're going to continue working on an n.h, which is a deep learning framework in C that we've been developing for quite some time, so this is our main project, so to speak. And today I would like to address the memory management within that library. You can find it in here. I copy-pasted it in the chat for people on YouTube. It's going to be in the description and stuff like that. Right, so today I would like to focus on memory management within that library. And the memory management right now is actually very straightforward, right? So the idea was that you just pre-allocate as much memory as you need for working with the specific model, for training specific model, and for using specific model, and that is basically it. Right, so there are such functions as alloc, right, so which allocates a neural network with a specific architecture, right, and architecture is described by sequence of numbers, I'm sorry, right, sequence of numbers. And also you can just allocate the matrix with rows and columns, and that's it. So you're supposed to just pre-allocate everything. Right, and just use it, including intermediate stuff, right? For instance, you have back propagation, right, which computes the gradient into a second variable in here. So you're also supposed to pre-allocate that. Right, and the problem with this approach is that it's actually not particularly flexible and not particularly intuitive, right? I would like the cool thing about Python is that it has a garbage collector, right? So that's the cool thing about it, is that you can just just describe what you want. You can just write what you want to write and then think about memory management and just forget about it, and the garbage collector is going to take take care of all of that. It would be kind of nice to have something similar in our framework as well, right? I want to be able to just do some computations and just quickly allocate a matrix in the middle of a computation for an intermediate stuff and just throw that matrix away. But since I'm forced to pre-allocate everything I'm gonna need up front, I need to sort of see in the future and see that I'll need that extra matrix somewhere in a different place of the program and pre-allocate it for that, and maybe even pass it through all of the arguments, through all of the call stacks and stuff like that, which is kind of annoying, right? And that's why in Python it is so pleasant to program, right? Because you can just do that. You can just allocate an intermediate matrix, do some computations, and just quickly throw it away, and the garbage collector is going to take care of all of that. Right, so, and we can have that in C, in fact. In C, we can have the same level of convenience if we implement something called arena allocator or region-based allocator. It has different names, but it's just like a linear allocator, right? So if you want to learn more about this kind of stuff, I just recommend you to Google up arena allocator, right? And there's a Wikipedia article which also links to some papers. It's called the region-based memory allocator. So it has, excuse me, several names. I'm going to copy paste it in here. I actually implemented region-based allocator on my stream several times, but for different projects and under different topics, right, so to speak. So I'm going to copy paste this entire thing in here just for anyone who's interested. So, and essentially the idea is you basically allocate a region of memory, right? So let's actually go ahead and straight up introduce a region of memory, right? So maybe I'm gonna go somewhere here where we start working with the matrices, and let's just straight up start writing a structure called region, right? So, and that region is going to have a certain capacity, right? So it's going to have a certain capacity, and it's going to have a certain size, right? So how much of that capacity is already taken? How much of that capacity is already taken? And then we're gonna have the data itself, right? We're gonna have the data itself. And essentially, you just pre-allocate big enough chunk of memory, right? You just allocate big enough chunk of memory, and you basically, every time you need more memory, you just take sub-chunk of that, and that's it. So, and essentially, every time you need an intermediate object, you just allocate that object into this region, right? And then at the end of some iteration, because you're going to have some sort of loop, like training loop. And at the end of the iteration of that training loop, you can just swipe out the entire region and start again. Right. That way, you may have a convenience of a garbage collector where you can just, in the middle of a complicated computation, just allocate a quick matrix, do a quick intermediate computation, and just forget about that matrix. You don't even have to call free. Right. You can just leave that thing in that region, and then at the end of some iteration, it's going to be deallocated at once. That's kind of the point of these linear region allocators, right? And I want to build memory management for this library around this kind of stuff because I feel like it's going to be very useful, because this is exactly what you want to do quite often. Just quick intermediate things that you can forget about, right? And region allocators are really perfect for that, right? And again, that's probably why Python is so great for, you know, scientists and mathematicians, because they do this all the time. Yeah. Right, and essentially, how would you even allocate, you know, something into that region, right? So we're going to have some sort of a function called region, which accepts the region into which you want to allocate something and the size of the object that you want to allocate. So this is going to be a malloc, but it's a malloc that allocates into the region, right? So there we go. So let's actually implement this specific function. Let's actually implement this specific function. So the thing is, region has a limited capacity. It has a limited capacity, and that's why we keep track of that capacity. So the first thing we need to check that the size of the region plus the size of the object that you want to allocate is actually less or equal to the capacity of the region. Right, and only then we'll be able to basically create a result, right? So result is basically the end of the allocated region, right? So maybe we can even draw that out, right? So essentially we have, let's say, this is the region, right? So each individual dot in here is a byte, right? So this is a byte. And essentially some of the bytes, we can replace some of the bytes with, you know, hashes like this. Replacing region with hashes, and it indicates how much we already allocated. So if we do something like data r count, what effectively is not count size, I'm sorry, effectively points at the byte in here, right? It points at the byte in here, and this is precisely where we want to allocate the chunk of memory of the size, right? So starting from here. And after that, we just return this entire thing. But before we return this entire thing, we want to mark the region that we want to allocate as allocated, right? So we want to do the following thing, like so. And we want to move this pointer to here. So this is the new place where we want to allocate, right? And we can do that by just adding the size of the chunk that we want to allocate. And that's it. That's the whole implementation of this allocator. That's it. Seriously. So, you know, quite often people might be amazed, like, how you are implementing your own allocator? This is so complicated. You need to have a PhD in computer science to implement your own allocator. You need to know how computers work. How we can do this? That's it. Three lines. Okay, 4 with return. Sure. So it's that simple. It's that simple. And this is the allocator into which you can just like throw some objects, right? But the problem with this allocator is that the object that you allocate, you cannot deallocate it. You cannot deallocate that one specific object. What you can do, you can deallocate everything at once. Right, you can deallocate everything at once. And the operation of deallocating everything at once, I think we're going to call it reset, right? So this is going to be reset. It's such a simple operation that I'm not even sure I want to have a I want to have a separate function for that. Maybe it's going to be literally a macro. Let's call it a macro. And the operation that deallocates everything at once looks like this. It takes the size and sets it to 0. Right. Can you do that? Yeah, you should be able to do that. There you go. That's how you free all of the objects that you allocated into that specific region. You just say nothing is allocated anymore. So essentially, physically, those objects are still in the memory, but they're going to be overwritten on the next allocs. Right. So they're going to be overwritten on the next alloc. And that's how we mark them as free. So allocation is super quick, and deallocation is also super quick. Right. So here's an interesting thing. You may notice that a region kind of looks like a dynamic array, right? It kind of looks like a dynamic array because this is how we usually define them. You have a pointer to the beginning of the region, right? To the beginning of the region. And then you have how much you already allocated, right? So with malloc or with some other allocator. And this is how much you already consumed. So here, when we ran out of the region, we actually assert, we actually crash. But in case of a dynamic array, we actually reallocate the whole thing to a different place. We can't do that with a region allocator. We literally can't do that, because if we reallocate, all of the pointers that point at the object that you allocated into the region are going to get invalidated. That's right. So one of the downsides of this kind of like approach is that you cannot extend the allocator. You just cannot extend it. There is a solution to that. Essentially, you organize your region-based allocator as a linked list. Right. So you decide that your single region is going to be, I don't know, like 16 megabytes. Or something. You allocate like a big region, 16 megabytes. And when you run out of that region, you allocate another one. And so essentially what you do, you're going to say, okay, so you also have a next. So, and your entire allocator basically just checks, okay, do we have any space in that region? All right, let's try next region, and so on and so forth. And resetting such region is basically iterating through all of these regions, linked list of regions, and setting their sizes to 0. But since these regions are so huge, you're not going to have too many of them, so the linked list is going to be very small by itself, right? It's a small linked list of huge pages of memory, so that's what it is. That's why it's kind of like, okay, but it kind of solves the problem of overflowing and not reallocating and stuff like that. So, and we're not going to do that actually, because it introduces too much complexity that I don't want to deal with right now, right? So I think we're going to go with the approach that just pre-allocate the region of the memory that you know is going to be sufficient for your problem and call it a day, right? And if you overflow, it's going to crash, you just extend the memory, right? So, or if you are on 64-bit machine, you can even pre-allocate a region of 1 gigabytes. Right. So because on 64-bit machines, on modern like machines, if you map 1 gigabyte of memory, it doesn't mean that you're gonna, you know, take the entire gigabyte of memory. So the operating system is not gonna start committing those pages of memory until you start using them. If you just say, okay, I want to use this gigabyte of memory, but never use the entire gigabyte, you're never gonna consume this entire gigabyte, right? So because of that, on 64-bit like modern machines, it's actually not a problem. I think we're going to go with this kind of approach where we have just a single region and we allocate everything in there and just like forget about it. Right. 99% of my memory management in C++ is just this. Yeah, that's the most pleasant way to manage memory, I think, right? Especially if you, yeah, after many years of software development, right, you need like, for some reason, you need a lot of experience to appreciate this memory management, right? So I tried different things. I tried the C-style memory management where you do malloc and free manually. I also worked with array AI. I also worked with garbage collection, and it takes a lot of time and experience. You need to experience all of the pros and cons of different memory management styles to kind of appreciate the simplicity of this thing, right? So a person who only started programming like 2 years ago and the only experience they have is Python, they would not fucking understand why am I so excited about this stupid shit. Seriously, like a person who had like few years of programming in Python, they unfortunately won't be able to appreciate this kind of thing. Like you need to go through all of the circles of hell of memory management, of different languages, of different approaches to just come to this conclusion. And that's why this thing is so difficult to sell. Like I can explain you the whole thing, I can explain you why I'm gonna use it, but if you just don't have the same amount of experience, you just will brush it off saying that I'm C boomer who doesn't understand what the fuck I'm talking about. You know what I'm talking about? Right? So a lot of things that I actually explain are kind of difficult to sell unless you went through all these circles of hell and understood why you probably want to do something like this. Right? So... So, and I'm not actually blaming those people, right? So I'm not blaming people for not being able to appreciate that. It is totally fine. It's just like you have to go through a lot to appreciate that. So if you can't appreciate it right now, that's fine. You eventually will. Don't worry, whether you like it or not. Anyway, so let's continue. Yeah, we're not going to be doing the linked list stuff, right? So we're going to have just like this simple thing here, right? And by the way, maybe there is something better, right? Maybe there is something better than this. I haven't discovered it yet, so I don't really know. Maybe I didn't go through all of the circles of hell to realize that maybe even this is not particularly great and there's something even better, right? So, but we'll see. We'll see. I don't know. I actually wouldn't say that I'm that experienced, right? So there's definitely a lot of people who are way more experienced in programming than me. All right. So, but what's interesting is that region alloc is allocating memory into the region. But how can we allocate the region itself? Right, how can we allocate the region itself? So the problem here is that I have things like mat.alloc that allocates the matrix itself. So according to the conventions that I implicitly set up for myself for this library, the thing that allocates the region itself has to be called region alloc, right? Because I already have mat.alloc, I already have nn.alloc, right, and they allocate the objects themselves, right? So they allocate them with, you know, an nmalloc, which is a macro that you can substitute with something or whatever. So I can't just use region alloc. I can't just do that. So it's sort of like allocating the allocator, right? What we're doing here, we're allocating the allocator. So it's a meta allocation. So what if we call this region alloc? And what we're essentially doing in here, we're doing the capacity, right? So essentially with alloc, you are allocating the allocator, and then you're allocating within the allocator with the region alloc. Right, so I think it's a good name. So it's a little bit long, but you're not supposed to call it very often. You know what I mean? You're not supposed to call it very often. You're supposed to call it like once at the beginning of the main, right? So, and that's why having a longer name is probably fine, right? You're allocating the allocator, and then you just allocate within the allocator, right? Let's actually go ahead and implement this entire thing. So, and we provide the capacity, and that's the capacity you want to probably allocate. What we're going to be allocating with? We're going to be allocating with nn.alloc, actually malloc. So it's a special macro that kind of allows you to substitute the allocator, the sort of like a low-level allocator of the library, right? So by default is malloc, but if you the user of the library want to replace it with something else, you can do that by defining an malloc. So that's why allocating the allocator is going to be done with a lower level allocator malloc, like this. So we're allocating the capacity, right? And so that gives us the data essentially, right? And we want to also make sure that the data is not equal to null, right? So because that thing may fail, right? That thing may fail. Okay. So this is an assert, and let's actually prepare the region. So this is the region, and the region itself has such fields as capacity, right? So this is the capacity. And the data, right? So, and we just set them up, and after that we can simply return this entire thing. So as you can see, we allocated the allocator. All right, so do we need anything else? So we're able to alloc, reset, and so on and so forth. We can try to maybe now do something with all of that. So another thing I would like to actually do, right, I would like to allow maybe to supply null instead of the region in here, right, to supply null instead of the region in here. So it will make sense if we just try to integrate that allocator into something. So for instance, if you want to allocate a matrix, you have to supply the region into which you're going to be allocating, right? So let's actually say that the matrix alloc now accepts the region. So you are only allocating into that region, which is actually kind of a cool interface. Like, remember that I said that I want to concentrate the memory allocation within a few functions, but there was a problem that it was not obvious which functions are doing memory allocation. Now it becomes obvious. If your function accepts a region, it's probably doing memory allocation, right? So maybe it serves as a documentation or something. I don't know, maybe. So, and let's actually find the matrix alloc. Right, so it accepts the region R. It accepts the region R, and now instead of doing an malloc, we have to do region alloc, and we just supply this entire thing in here. Right, so that kind of limits you in terms of how you can allocate your matrix. You can only allocate your matrices on a specific regions. But what if you want to just allocate it with malloc? What if you just want to allocate it with malloc? I think we should allow you to still do that. Even though we're moving towards like region-based memory allocation, it would be nice to allow users to use malloc anyway. So the idea that I have for that is essentially, if you try to alloc, but you supplied null in here, we're going to use malloc, right? So essentially, if R is equal to null, just return and then malloc size. That's it. So I think that's a good solution, right? So if you just like put a null in there instead of region, you just use a regular malloc. Maybe that's what you want. Right, maybe that's what you want. So that gives you sort of like a flexibility into how you can do this kind of thing. And furthermore, you can even substitute and then malloc itself with something else. We will give you a shit ton of flexibility. Like all of the things in here are replaceable, right? Malloc is replaceable. Region, like you can allocate a region. If you provide null, you still allocate it to malloc. Malloc can be replaced. Everything can be replaced. This library can be thrown away if you want to, right? Right. At some point, you can just switch to Python and use PyTorch. That's how flexible it is. This library is so flexible, you are allowed to just not use it. How many libraries allow you to just not use that library? No. Like, you go into the marketing of any library, they will tell you why you must use this library. This library is so flexible, it allows you to not use it. That's the level of flexibility no other library will give you. Oh. Alrighty, so that's what we've got. That's what we've got. Alright, and when I'm doing this kind of thing, right, so I can do matrix alloc. So this is a matrix alloc, and we're allocating everything. We're also checking for an assert. Right, and it still makes sense to check for an assert because you may supply region null, and the malloc in here can still assert, right? It can still assert. Interestingly, nah, it's fine. So one of the things you can have in here, right? So one of the things you can have in here is that user can replace and then assert. User can replace and then assert, and they can replace it with nothing, which effectively deletes all of these runtime checks, right? So this is one of the options that you can have. In that case, the region overflow stops working. So maybe in that specific case, we still have to check this thing. So essentially, if the sum of the size overflows, we simply return null. Right, there we go. If user will delete this assert, if the user deletes this assert, it still returns null in here, right? Now the time has come for a little bit of a compiler-assisted refactoring because we changed the signature of this thing, and we want to start with the refactoring the demo. So I'm going to start with the simplest one, Zor, right, because it doesn't use much. It's a very simple demo. Right, we can even try to run this entire thing. So it's going to be demo Zor. Right, so there we go. So this is the whole demo. Right, it's very simple. And what we are going to do, I'm going to limit the building to that specific demo. Right, so I'm going to go through the compilation errors of that demo only. Right. So there we go. As you can see, when we're okay, this is actually kind of cool. So that affects the function that loads a matrix from a file. We don't really use that function very often, but yeah, so it used to allocate things, right? So it basically tries to read the file, then it sees that in file there is a matrix of certain size, and it just allocates the memory of that certain size. And it makes it super easy to just like control the allocation of this entire stuff, right? So that means I can provide this entire stuff in here, and that means I need to change the signature of mat load, which introduces even more compilation errors. So this is how compiler-assisted refactoring sort of cascades. You're trying to fix one error, you introduce more and more, but then at some point they start to collapse and you have the entire thing refactored, right? So you have the entire thing refactored. All right, so let me see what we have in here. So now we have an analog, right? So because to allocate neural network, you need to allocate matrices, and now you have to allocate them only in a region. So that means an analog also has to accept a region within which you're going to be allocating all of that, which effectively modifies its signature here as well. So as you can see how like a simple change starts to chain, and it's just sort of like a cascade, like an avalanche, right? So, but the thing about compiler-assisted refactoring is that you should not be scared of that process when you're refactoring. You should control the avalanche of errors, right? So, and it actually takes a lot of experience, because you can overdo this entire thing and it can grow exponentially indefinitely, and you will be constantly in a state of your code not working. So you should be actually not trying to do several compiler-assisted refactorings simultaneously. This is the mistake that I quite often do. For example, I set up a specific goal, right, to change the signature of this function. While I'm changing the signature of this function, I may notice that, oh, I would like to change something not related to this function and introduce another cascade. That introduces even more problems, and now you're managing two compiler-assisted refactorings. Is it clear what I'm talking about? I'm not sure. But this is something that happens to me quite often. There is this temptation to start refactoring something else while you're refactoring the one thing. And this is where the problems like creep in. So you're starting to manage too many things, right? So it's a mission creep, yeah, exactly. So that's why you have like, you need to have a lot of experience and discipline in doing this thing to stay focused. Okay, I'm refactoring only this thing and I'm changing only these things to just like facilitate that, right? But at the same time, it's kind of useful if you want to change something to maybe put it to do. Right, so like you notice some, oh, I want to change that, but if I touch that, that will create even more problems. I'm going to put it to do, and maybe eventually we'll come back to that, right? So that's very important. That's very important. Anyway, so now here I already passed a region, so that means here, yeah, that's fine. Oh, and this one is very interesting actually. As you can see, we're also using malloc directly when we're allocating neural network. Right, so, and this is needed for sort of like arrays of arrays, right? Because in the neural network, we have these arrays of matrices. So we're allocating matrices within the region, but the arrays themselves are not allocated within the regions. And maybe this is something that we want to fix, right? So let's go to NN alloc. Maybe I'm gonna actually go through all of the places where we use NN malloc, right? So how many places we use that? In NN alloc, right? So in the region alloc, and in the region alloc. Okay, so ideally, if we did everything correctly, we should only call to the like lower level malloc in things that are related to regions. Everything else should go through the regions, right? Everything else should go through the regions. The only mallocs that we call outside of region related stuff is NN alloc, right? Everywhere else, yeah, this is the only three places. Okay, this is fine then. So that means we can do a region alloc. So this is R, and that is it basically, right? So this one is kind of weird. Let's replace it with 1. So this is one thing, and this is a matrix alloc, and we're going to be allocating it within that specific region, right? So we're allocating all of that within that specific region. Okay, let's try to recompile. So what else? This is, okay, I forgot to put this thing in here. Okay. Result. What you don't like. Incompatible conversion. This is because I need to take a pointer to that place, right? So I taken basically the value at the tip of the region, but I don't take the pointer. What we need in here is actually the pointer. We don't really care about anything else. Okay, and we're actually went out of the library. So now the demo is failing. Right, the demo is failing. So in this demo, as you can see, we are allocating just a matrix, I suppose data matrix. It's a training data for the XOR, right? And it wants a region, right? It wants the region. So let's actually go ahead and allocate some regions, right? So, and what I want to have actually, I want to have two regions. I want to have a main region, and I want to have a temporary region. So in the main region, what we're going to store the training data and the main neural network, the main model that we're training, because these things have to live for the entirety of the whole program. We may actually, maybe we should even allocate them in like with null, right? By setting the region to null. Maybe it's going to be, yeah, convenient. So the main thing that lives for the entirety of the program is going to be nulled. Right, and we're also going to have things that live only for the single iteration of the event loop during the training, right? Because during the training, we pre-allocate temporary things, for example, a gradient. Excuse me. A gradient is a neural network, the parameters of which are differences that you have to add to the main neural network to actually improve its cost function. And that neural network is actually temporary. It's an intermediate calculation, and we should store it in a temporary memory, and it should be for a single event loop, right? So that's basically the idea. So, and we're gonna, for this kind of stuff, we're gonna allocate a temporary region allocator. So we're gonna do region alloc, right? So because we're allocating the allocator, how much memory we want to allocate? I don't know. Let's allocate 256 kilobytes, megabytes. Let's just allocate like a huge, like we're definitely not gonna use all of the 256 megabytes, but why not? Let's the modern machines actually allow us to do that, and it's not like the actual program is gonna use all of the 256 megabytes, right? Because if we never touch this memory, it's never gonna be committed, right? So yeah, so I think that's a very good approach. That's a very good approach. In fact, this is such a useful approach that I think in Jai, there is something like that, right? If you take a look at Jai, they have a pool allocator. In fact, they have two pool allocators, I think. Right, yeah, so there is a regional pool allocator, which is literally the region that I just described. So it's a memory allocator that you can use when you want to quickly allocate memory blocks of many different sizes, right? And as far as I know, pool is like literally a linked list, or maybe they use something else, but it's just like it consists of these like huge chunks. Yeah, so there is a memory blocks. Right, so it operates on the level of memory blocks, and it also keeps track of the current memory block. We can take a look at what's the memory block. There you go. It is basically the region. It is basically the region, right? So then next memory block. This is literally what I was talking about, right? And then at some point, John introduced a thing called flat pool, right? So this is a new simpler version of pool that uses the 64-bit address space to achieve this simplicity, right? So, and essentially the idea here is that you just like allocate a huge thing in here, right? And I think the default virtual memory size is 256 megabytes, and this is probably what actually influenced my decision, right? So I sort of probably it went into my subconscious, and I subconsciously like set the same size in here as John did in here. Yeah, there we go. So it's such a useful thing in 2023 that John also introduced it in the language, right? So yeah, if the modern hardware allows you to just like allocate a huge chunk, and also modern operating system, why not take advantage of that? Like, it just makes everything easier. It just makes everything easier. All right. Okay, so let's just also allocate 256 megabytes, and we're allocating the training data with malloc, with just regular malloc. So we generated the training data. So here we split the training data into inputs and outputs. And now we're allocating the neural network, right? So we're allocating the neural network. And this is probably, yeah, we want to allocate it with just null, right? So we want to allocate it just null. And everything else is going to keep working as usual, I'm pretty sure. Yeah, there we go. So we just basically refactored, but nothing particularly changed, right? So the temporary allocator is not really used for anything. Right, and this is because I want this entire thing, like specifically in terms of backpropagation, to not accept the gradient. Right, I don't want the backpropagation to actually accept the gradient, because the gradient is the output of the backpropagation. It's the output, so it's an output parameter. And now having temporary regions allows me to emphasize that it's an output by returning the gradient. So now backprop can allocate this gradient into the region and return this thing to you. And now you know that this thing is an output parameter. So it's sort of like, you know, it emphasizes the intent, right? Before, when you were accepting this kind of thing, it's not clear what's the input, what's the output and stuff like that. But now the gradient is a return parameter, and you can clearly see that. So this is one of the reasons why I introduced this kind of thing, because it allows me to do this kind of thing, right? And since it's going to be allocated in a region, like in a temporary region, it can be basically reused on the next iteration. So everything should work fine. So let's actually go to backprop implementation and literally replace this entire thing with that. And that again breaks the whole thing, right? So that again breaks the whole thing. So let's actually go through all the compilation errors, and there you go. Okay, so we don't accept the G anymore, right? We do not accept the G anymore, which means that we have to create it, right? So we have to allocate it within the region. And here is an interesting thing. Here is an interesting thing. To allocate a new neural network, you need to know its architecture. You need to know the architecture of the neural network, but we don't actually store the architecture of the neural network anywhere. So when you construct a neural network, its architecture just used to allocate the matrices of the corresponding sizes, and then it just gets thrown away, right? So the neural network itself does not store it. It would be kind of nice if I could just say, okay, allocate within the region the neural network with the same architecture as the one that we got from the parameters in here. So it would be kind of nice if the architecture was like inside of this neural network, and I could say, okay, so allocate the same neural network. But we can't do that because we don't store that architecture anywhere. We just throw it away. It would have been kind of nice, wouldn't it? Maybe. I don't know. So maybe we should try to do that. Maybe we should try to do that. So essentially, we can say, okay, so this is the count. And count actually, yeah, this is the thing. So we need to remember how we define the architecture. We need to remember how we define the architecture. So this is how architecture looks like. So it's a sequence of numbers. It's a sequence of numbers. It's pretty straightforward. So the first number is the amount of inputs. Then the sizes of layers, right? So then, as you can see, it has a layer, a hidden layer of the size 2, and the output layer with the size 1. So it has 2 inputs, 1 output, and like 1 hidden layer of size 2. And this entire thing essentially looks like this. Wait, just a second. I can... Yeah, there we go. So this is how it looks like. So this is the description of this architecture. This is the description of this architecture. Okay, and count essentially stores the amount of weights and biases matrices, which is effectively the size of the architecture. So the amount of numbers in here minus 1. Right. So what if we, what if we do a little bit of a switcheroo? And now count is gonna store the full sort of like architecture count, right? So it stores all of the numbers. And then in here, we store the pointer to the architecture. Right. So now, as you can see, I made a note in here that the amount of activation is count plus 1. Now, the amount of activation is exactly arch count, but it's the amount of BS and WS is count minus 1. Right. So now we need a switcheroo. So it's kind of interesting. Right. So why it is like that? Why it is like that? Because the matrices describe the connections between two layers. Right. You effectively have 3 layers in here. Three. Right. So the input, the hidden one, and the output. But the spaces between the layers, there's only 2 spaces between the layers. Here is the first space, and here is the second one. Right. So when we describe a neural network, we don't describe the neurons themselves. The neurons themselves, like, they're kind of useless. It's the connections between them. And the description of the connection is between the layers. Right. So that's why we have like a kind of a difficult situation in here. So the amount of layers is 3, but the amount of matrices that describe the whole neural network is actually 2. Does it make sense? Right. So, and because of that, it's like kind of difficult, like chasing the count. Right, so we're chasing this kind of count and stuff like that, right? So, yeah. So I hope it's understandable. Like it was all in the previous episode. So. So there we go. So, and this is quite important. That effectively changed the semantic of the count field. And this is why I want to change also the name of that field. You know why? Because now every place that uses this field is going to break if I rename it. And this will tell me that, oh, I also need to refactor not only the name of that field, but also a semantic. Because, right, before, it meant one thing, it meant the amount of the weights matrices, but now it means the amount of all of the activations. So all of the -1 +1 things should be changed as well, right? So through a compiler-assisted refactoring, by just renaming this thing, I'm also going to be refactoring the semantic of the whole thing. Right, so that's actually kind of cool, which will allow us to finally have this kind of thing. So where was the, I think it was in the back propagation. So here is the back prop. Right, so yeah, so here we have arch and arch count, and then we just zero it out. Okay, let's actually try to compile this entire thing. Let's try to compile this entire thing and see if it's going to even work. Surprisingly, it compiled, but this is because I didn't even try to compile. Okay, so as you can see, it fails everyone. Oh my god, okay. All right. So this entire thing failed in the UI framework. So this is the code that is responsible for rendering the neural network itself. It is responsible for rendering the neural network itself, specifically this thing. So this is the code. This is the code that renders this stuff, right? And we broke that code because that code refers to the amount of layers. So that makes sense, actually. That makes sense. Okay, so, but this one is actually rather easy, I think. This one is actually rather easy because count actually meant the size of the architecture -1, and that's why we were adding +1 in here, right? Just to accommodate one of the lost activations. So now we can just do arch count like that, and that's the same thing. And maybe we can even remove this entire variable and just refer to and then arch count directly, right? So that's one of the things we can do. So yeah, compiler-assisted refactoring is useful for also refactoring the semantics, right? We not only renamed the variable, we also changed its semantic, but we renamed it so we know where we have to refactor the semantic. Isn't it cool? Right? I think it's actually pretty cool. Okay, so let me see. So let's actually try to recompile one more time and see where else it's going to fail. Okay, so now every time I refer to arch count in here, I'm actually referring to an arch count. And that makes a lot of sense. Yeah. Okay, so it's already failing in unrelated places. And okay, so now it fails in a heat map rendering. Right, and a heat map, if I'm not mistaken, looks like this. Right, so let's actually find adder. Yeah, there we go. So this is the, yeah, well, we have two ways to display neural networks. So this is just like a fully connected graph and also like a heat map, right? So just depending on the size of the neural network and your model, you may choose like how exactly you want to visualize it. But these things, these two things are visualization of the same neural network, but with like different visualization techniques, right? So here is just like a fully connected, and here is the heat map of the weights and biases parameters and stuff like that. Right, so, and that place also broke. That place also broke. Okay. So here with, okay, so count was arch count -1. So that means we want to do arch count but -1, right? So that changed the semantic of this entire thing. All right, so try to rebuild it one more time. And this is a kind of a similar thing. So because count is the arch count -1. So do we have anything else? Also arch count -1. What else do we have in here? So render activation heat map. And count +1 is just arch count, which means that I can replace this thing with arch count. Right. There we go. This is how we can effectively use the compiler for refactoring, right? With just a text editor, right? It's just a text editor. You don't need like any IDE or anything like that. If you just stuck with a text editor and a statically typed compiler, you can, you know, exploit that compiler to do pretty sophisticated refactoring techniques that would have been possible if you, like, you know, didn't have that. Anyways, so what else do we have in here? So NN output, and it complains about, oh, okay, so it failed within the macro NN out. Okay, this one, all right, this one is interesting. So the neural network itself also contains the matrices for intermediate activation, right? So when you forward data through a neural network, it activates each individual layer. And for the intermediate stuff, we store these matrices in here. This is an interesting thing. The activation matrices within your neural network are intermediate things as well. Which means that maybe we could remove this entire thing and let the place that forward stuff to just allocate these intermediate activation matrices and then just forget about them like in the next iteration or something like that. But again, this is getting closer. You know what I'm talking about? This is precisely what just happened. Like I'm refactoring just adding arc and arc count. But while I was doing that, I accidentally wanted to also remove this thing. And I always like fell into the trap of starting another compiler-assisted refactoring without finishing the first one. I almost deleted this thing. I literally wanted to delete this thing and go to all of the places where I use all of that, and I almost created a disaster. This is precisely what I was talking about, right? So it always, the thing about this compiler-assisted refactoring is that it always tempting to start a lot of them, start refactoring, because you get all of these ideas that you want to actually implement, but it's super dangerous because you can basically end up in a dead end, right? Because you started too many things and you have your code completely broken, right? So instead of removing this kind of thing, I would like to put it to do. Let's just like not rush too much, right? Let's not go on that refactoring yet. Maybe remove this as remove this. We have, it would be better to allocate them in a temporary region in a temporary region during the actual forwarding. Yeah, something like that. Right. So let's not create too many compilation errors, otherwise it just gets unmanageable. As soon as you start two parallel compiler-assisted refactorings, the compiler will basically switch between different branches of refactoring, and you will just lose the context, right? We'll just like lose the entire context, so it's kind of dangerous, right? So let's go further. Right, so it was failing in here. So essentially now we have arch count, and essentially arch count is arch count -1, right? So it means I can just like replace it with -1, like so. Here's an interesting thing. I think maybe this is super dangerous, isn't it? Right, you're just accessing the element directly, but what if the amount of elements here is actually 0? What if it's actually 0? Maybe it would make sense to just check and then assert something like, and then arch count is greater than 0, right? So, and we're using a comma operator in here. Do you guys know about the comma operator in C? Do you guys know about it? So the operator, essentially the sequence operator, right? So we can write some code, main.c, and let's actually do main, and we can do printf, right? Let's print a number. Let's just print a number. And what if I do something like printf hello, printf world 69. So what will this program print? Is this even a valid C program? I'm sorry. Why do I? What the fuck is this? Is this Hebrew? I don't know. Right. So what's going to happen? Yeah. So the first thing that chat actually asked, is this even legal? Like, what the fuck is going on? Why the fuck would you even write like that? Is that even C? I'm pretty sure it's not going to compile, right? So what the fuck is that shit? I'm sorry, Zozin. What the fuck? You're crazy. The fuck? This shit just compiled. Like, I'm telling you, like, I keep telling that over and over again. C is such a simple language. It's way simpler than C++. But it's always something new with that motherfucker. Right. It's a mystery language. It's so goddamn simple, but the more you learn it, you always fucking discover something crazy about this motherfucker. It's just like where it's hiding all of that. Right, it's just like, what, is that a thing? You can do this kind of shit, and what does it even mean? And what the program is going to print? What the hell is going on? Like, what? Dude, this is this some magic? Like, it's probably an extension, right? It's probably an extension. Let's actually say, use std c99 and be pedantic about the standard. Is that even a standard C? Is this a standard C? What the fuck? This is literally a standard C. What the fuck is going on? So this is basically called like a chaining operator or like a sequence operator or something like that. So what's the idea? You can have in parentheses, usually, I'm not sure if parentheses are important, right? So, but essentially you can have expressions I think statements won't work, but expressions. List it like this. So expression 1, expression 3, expression 4, and so on and so forth. So let's actually say you're going to have expression n, right? So, and this entire thing is an expression. This entire thing is an expression. So you can have a type and you can assign it like this. So what's going on when you use this kind of construction? The compiler will generate a code that first evaluates expression 1 and forgets its result. Right, if there are any side effects within that expression, they're going to be applied. Right, then it evaluates expression 2 and forgets its result. Evaluates expression 3, forgets its result. And then it evaluates the last expression, and the value of that expression is the value of the whole expression in here, and that's the value that's going to be assigned to this specific variable. So this is how this entire thing works, right? And this is why the code printed what it printed, right? So if we take a look at this entire thing, right? So I'm going to actually print, do main, there we go. So first it printed hello, right? Because it tries to do print, so it needs to first evaluate this expression to get a value of that expression to put it in here. So while it was evaluating this expression, it evaluated this thing, right, and that had a side effect and it printed hello. Then it evaluated this thing and that had a side effect and it printed world. And then it evaluated 69, that was the last expression and that was the value of this entire expression. And that effectively gave the number to this printf, and this, the last thing it printed is 69. That's why it worked like that. Right, and it's kind of useful in case of the macros, right? For example, I have a macro that accesses an array within the structure, right? But what if the array is empty within that structure? One of the things we can do, we can basically put assert in here. So first we check whether we have any numbers in here, and only then try to access that number. So it's basically like a array in like access check. So, right, and since an n input is expected to be an expression, right, it's going to work, right? It's sort of like a compound expression, in a sense, like a compound expression. So it's still an expression, but it now has an extra side effect that checks that you don't go out of bounds or anything like that. Does it make sense? Does it make sense, meine Freunde? Does it? I hope it fucking does. Because otherwise, doesn't make any sense. So I'm gonna fucking ban you. I'm joking. I'm not gonna do that. All right. Let's continue. Let's try to recompile this entire thing. Okay, so this is not. I'm compiling the previous example. I need to compile the demo, right? Because we're going with the compiler-assisted refactoring. And here is an interesting thing. So that also failed within the function where we allocate all of that. Right, so now what we have to do, we have to assign arch, which is just arch. And this is the architecture that we're accepting in NLLog. So essentially now we can just save that, right? So we can just save this architecture and that's it. So that was relatively easy, I think. That was relatively easy. And now, okay, so this is architecture, but this time this has to be -1. So this is going to be arch -1. And arch is actually +1. So it's we're sort of reversing this entire thing. Okay, so when we're filling neural network with zeros, right? When we filling the neural network with zeros, we're just doing that. So I suppose we just have to do that. And here, this is going to be arch -1. Right, and it's quite important to go through all of the instances of this thing because the semantic has changed. Right, so because now it is -1. This one is also -1. I hope that I didn't make any mistakes anywhere because otherwise it's going to be disastrous because this is C. All right, so, and it's equal, right, which means that I can do arch count less. Right, I can just do arch count less, and that makes sense because I'm iterating through the Yeah, through the activations, right? I'm iterating through the activations. All right, so this one is arch count -1, right? So here's the interesting thing. Like, I don't even know what this entire code does, right? So that's the thing about compiler-assisted refactoring, right? So when it fails, I don't even look at this code. I don't even look at this code, right? The only thing I know is that that specific place has failed for whatever reason. Where was the, yeah. This specific place has failed for whatever reason. And the only thing I know is that instead of count, I have to do arch count -1. And that's it. Right, and I don't try to understand this code or anything like that. Like when I'm in a compiler-assisted refactoring mode, I have like a sort of like a tunnel vision. Like I don't see anything except one little thing that I have to change. And then once I change it, I just like move on to the next one. And that's why I can just like quickly identify, okay, I need to change this to that, and so on and so forth. Right, so I know that count is arch count -1. That's it. Right. So everything else, it just like doesn't matter. Okay, so where does, okay, this one is interesting. We are in a backprop, and this is one of the situations when I do need to actually think now. Right, so we were accepting the gradient as a parameter, but now it's an output parameter. We allocated it within the region and just computed it, and now we have to not forget to return it. Right, so now we're returning this entire thing. That's cool. Right, everything where is going to be deallocated on the next iteration. Okay, so this is finite. Okay, this is finite differences. All right, and also finite differences are similar to backpropagation. The finite differences are also similar to backpropagation in the sense that they should return. Yeah, okay, I'm getting to right. I want to go into another compiler-assisted refactoring. So I'm refactoring only the backpropagation. Right, so what I should do is probably refactor and then finite diff, right, to return nn, just like and then backprop, right. To be fair, I don't think finite differences are used that heavily, so starting like a parallel compiler-assisted refactoring on that thing is not gonna create too much problem, but I still don't want to risk it. I don't want to risk it for the biscuit, so let's not do that. Right, so here we're just gonna do arch count -1, right? Also arch count -1. Okay. So, and here we're doing backprop. And we're using backprop in a batch process. We're using backprop in a batch process. And if we take, this one is rather interesting. So I'm thinking, I'm gonna probably do that a little bit later, right? So I'm probably gonna do that a little bit better, but batch process should probably never even accept the gradient. Because if you take a look at any of the demo that uses batch processing, right? Batch processing, right? It accepts G, but G itself is never used anywhere, right? So essentially, batch process just like uses gradient, allocated memory for the gradient, and then after that, outside of batch processing, it's never needed. So maybe for the batch processing, this gradient thing could have been a temporary thing that would live for the entirety of just like a single batch process. Yeah. And that way, the users of the library would never have to allocate the gradient themselves, right? So because one of the things we were doing all the time before like actually training things, we were allocating the neural network itself. And we're also allocating a gradient because it's needed for intermediate computations. But now that intermediate computation is abstracted away. We may never even know that more memory allocated to just compute that gradient, like we don't care. That is so cool, but it requires refactoring even more. So that means we need to refactor batch process to not accept G. Right, so to do refactor batch process to not accept gradient G. Right, I'm gonna put this thing in here. So, but doing that will start another chain of you know, compilation errors. So I probably don't want to do that right now. So I'm gonna put it to do. So backprop, yeah, it returns G. It returns G. Right, it returns G. But that means we don't even need that G anymore, right? So we probably have to start refactoring batch processing a little bit earlier. We have to start refactoring it a little bit earlier. All right, because we just use that, but then it's just not needed anymore. God damn. All right, I suppose we have to start refactoring this entire thing a little bit earlier. So we're just gonna remove the G, right, and I'm gonna remove the G. And so we're starting refactoring it right now. All right, so as you can see, too many arguments. Yeah, so we need to accept, we need to pass the region now, right? We need to pass the region. And that means that we have to accept the region for the batch process here as well. Right, so this is going to be the region, there we go. So what else do we have in here? Okay, so we are in XOR, so we have to now finally we have to supply the temporary allocator in here. Right, we have to supply the temporary allocator, and so we should not supply the G. Right, so we're going to be accepting G in here. So this is a completely different thing. All right. Okay. So and it says that this G is never used. Yeah, that's precisely what I'm talking about, right? Because we don't have to do that anymore because it's now an intermediate value during the back propagation. Okay, so that's cool. And everything seems to be compiling. But this is a little bit dangerous, right? So let's try to also print how much temporary memory we use during the training, right? So temporary memory, memory. So this is going to be 0 bytes. Like how many bytes do we use for all of that? So let's say, so this is going to be temp, and temp is essentially like count. I think count, its size is the amount of bytes. Like it is literally amount of bytes. All right. So it is compiling, and let's try to run the XOR. Right, let's try to run the XOR. Here's XOR. Okay, so as you can see right now, we're using 0 bytes of temporary memory. Let's try to start training. And it keeps increasing because we never reset the memory. Right. So we're just keep allocating shit into that temporary allocator, but we never reset it. It's this is so cool. Look at it. It's literally that. It's fucking literally that. Because we're allocating memory in the loop and we never free it, and it's just like anyway, so the thing we need to do actually, right? We need to reset the whole thing at the end of the iteration, right? So, and we already have the reset, right? So if we do region reset, it just sets the size to 0, right? It just sets the size to 0. So region reset and reset the temporary allocator. But here we kind of, do we assume it to be a pointer? Yeah, we use an arrow in here, so that means we do in fact assume it a pointer. So, but this is actually kind of cool way of measuring temporary memory, because we just allocate as much as we want. We then first print how much temporary memory we allocated on one iteration, and only then we reset. So at any point, this thing is going to show how much memory we consumed for a single frame, right? Because we're freeing the memory on each frame, and this is how much we like consume the memory on a single frame, which could be useful actually, right? Which could be useful. So let's actually see how it's going to look like. So I think it is in fact rather useful to do it like that. I think it is rather useful. And yusu. So let's actually start XOR. And okay, that's cool. And when I stop, it actually says 0, right? So, but it consumes 28 kilobytes, 29 kilobytes, almost 29 kilobytes on each frame. Right, but then if you stop, it consumes actually rendering the frame, so it just like deallocates it. But overall it works, as you can see, overall it works. Right, so we have a temporary arena, right, and we can do all of the intermediate computations within the temporary arena now, right? So, which may make using this library a little bit easier in the future, right? So, because being able to just like do intermediate things and not think about memory management is kind of important for a programmer, in my opinion. It is in fact kind of important. Right, so, and now you'll be able to just say, okay, well, here is the 256 megabytes of temporary memory, and just like use that. And then you can, you know, clean it up on each individual iteration. So we only refactored Zor demo. But we also need to refactor the rest of them, right? So we have Ada, right? So which also uses the old API. It still uses the old API, and is essentially also a very important image to NN, right? So we need to refactor those. But I think I need to make a small break before I do that and make a cup of tea. I think that's important. So let's make a small break and all right. So let's just turn off the music because I mean it's copyright and stuff like that. So let's continue refactoring the demos. So we refactored Zor, right? So it should be working. It should be working, right? So now it seems to be, yeah, everything's fine. So let's turn off Zor and try to refactor the Ada, right? And what do we have in here? So in the Ada, as you can see, we call to these functions that allocate the memory, but we call them without the region. Let's do region, and we're gonna be doing, so I suppose for this stuff, right? So for this stuff is gonna be null, right? So that's fine because it's a sort of like a permanent stuff. So here we have a neural network. I think it also has to be permanent stuff. The gradient, we don't even pre-allocate it anymore. It's an intermediate thing, right? So we forget about it as the pre-allocation. And batch process, yeah. So we're calling here to the batch process, and now we don't have to pass it. And so essentially allocating the gradient is confined within the batch process entirely. It is confined within the batch process entirely. So let me see. So this is the batch process, but it needs to accept the temporary allocator like so, right? There we go. So we don't have, didn't I not allocate? Yeah, so let's go ahead and allocate it. So this is gonna be region. So this is TMP and region region alloc 256, 24. There we go. What we're gonna do next. All right, so, and that's it. That was really it. And yeah, I think I want to also print the temporary memory. I think being able to print the temporary memory is quite important. Temporary memory, right? It's a useful parameter to actually have in here, right? It is in fact very useful parameter. So it's temp count, right? So a size. Yeah, I should have actually called it count because that's the usual reflex that I have when I'm typing these kind of things. Now we're gonna do demo Ada. There we go. So the temporary memory is 0. So how much memory we consume per frame? Yes, classic. I forgot to reset this entire thing. So region reset in temporary. So we just reset it to 0. And let's see how it's going to work. Let me run. Okay, so we're consuming 350 kilobytes per frame, right? So that's how much we consume. So everything's fine. So Adder is refactored successfully, I would say. Do we need to do anything else in here? I don't think so. Everything seems to be fine. And let's go to build.sh and refactor the image to NN, right? So the most interesting demo in here, I would argue. the most interesting demo. So here we are allocating the stuff, so we can do that. Gradient is not needed anymore, hopefully. The next compilation errors was going to be the next compilation error. So here we are allocating the training data, so it also has to be allocated with malloc, right? It doesn't have to be a temporary thing. And in here, right, so we just do a TMP, temporary stuff. So that also means that we need to allocate the region. So this is going to be temporary. Region alloc, and 256 megabytes. Looks Gucci, looks Atamaguchi. That was easy, right? So we didn't really change the API that much, right? So all of the demos are just fine. They're just fine. So when we do batch processor, so we do TMP, and of course, at the end of this entire thing, we want to reset the temporary allocator. And this can be temporary memory. So this is going to be temporary memory, ZU, and what is it called? TMP size. So let's rebuild it. Easy peasy, a lemon as squeezy. Demos. Where's the demos? Image 2 and then. So let's provide two images. MNIST training 8, MNIST training 6. There we go. So here we have two images and stuff like that. So if we try to now train this entire thing, as you can see, it is training stuff. And the amount of memory is actually stays sort of like the same. I think it became slower. Right, but we'll have to actually check how it works off screen. Probably because of the cache misses, right? So maybe because we're just like all over the place in terms of memory, that introduced like a lot of cache misses. So maybe that's actually the problem in here, but who knows? Maybe that will give us an opportunity to, how to say that, to profile all of that. So, Yesu, that's pretty cool. Okay, so the time has come to maybe do a committee. So there is another demo that I didn't really port properly, but I don't think it needs to be ported. It's a layout, but it doesn't use anything from nn.h, so I think it should compile fine, right? So, and we can do the final compilation, right? So just to check that everything is fine. So let's do committee. Did it just... Yeah, I accidentally saved compilation thing. Happens. Shit happens. So we don't need that. All of that is not needed. And yeah, we can now say introduce region allocator. Introduce region allocator, and let's actually push all of that stuff. So we can take a look at what are the stuff we have. So we introduced a couple of to-dos, right? So we may want to remove activations from the neural network, but I feel like it may take too much time to do this kind of refactor, because this kind of stuff is very integral to have the library works. So it may require like a lot of time just, you know, dismantling this entire sort of paradigm. So the other to-do we can refactor and then finite differences. Even though we don't really use it very often, we may still want to sort of bring it to the same interface as the NN backprop, right? Because finite differences is like backprop, but different. It's a different approach to computing the gradient, right? You can compute gradient using backpropagation, or you can compute it by, you can approximate gradient by doing finite differences. And because they're doing basically the same thing, or similar things, it makes sense for them to have similar signatures, right? Where it returns the gradient that it computes, it accepts the region within which it allocates all of that stuff, and it accepts the neural network and the data, but the finite differences on top of accepting all of that stuff, they also accept a small epsilon. It's just basically for like how much you have to wiggle the parameters of the neural network, right, to compute the gradient. All right. So, okay, A dumb question in uni. I'm learning Java, which has a garbage collector, but I never looked at it. But how do you decide write in C to do the same? I hope my question makes sense. How do I decide to use garbage collector? No, it doesn't particularly make sense. But to be fair, like, it depends how much experience you have in programming, actually. Are you learning programming? Like, how much experience in years in programming do you have? If less than 2 years, don't even worry about that. Just don't think about it. Just program in whatever your university teaches you, and program as much as you can, and develop different projects, different specific projects, like actual tangible projects, and don't think about that stuff. Don't even care. Seriously. Right. Just get first. Okay, so the answer is first year. Don't even think, don't even bother. This kind of stuff doesn't become important for you until you have like at least maybe 5 years of it. Like, just program, just get more experience, just get more skill. Just don't think about it, seriously. Just first learn how to program, and then go into this kind of deep topic, because it's a very advanced deep topic. Don't think about it too much. Seriously, you're only gonna hurt yourself. Right. You're only gonna turn yourself from programming. Just learn how to take the requirement and translate them into the code. Just learn how to be ChatGPT. Right. So yeah, just like develop project, like make a game, make a Tetris game, right? Or a calculator or something. It's just like, yeah. Nah, fact, ChatGPT dumb. It is dumb, right? And it's kind of weird that people only recently started to realize that, ChatGPT is kind of dumb. But it was not like that during the initial hype, right? It's just like, it's interesting to see how people are slowly getting more and more disappointed in it. It's really interesting. And I'm not sure if it's actually genuinely people getting disappointed in the technology, or it's just actually getting dumber. Maybe OpenAI is doing something with it to make it dumber. It's kind of difficult to tell. I think there was a discussion on Twitter, like people asking, is the ChatGPT like getting dumber? And somebody from OpenAI like jumped in and said that we didn't really change anything like since like that period of time, so it's just kind of stayed the same. But maybe they're lying. You can never trust them. Right, so I don't know. Is it getting dumber, or is it actually not that Use that crap maybe 5-10 times. Yeah, it is actually kind of fun at first, but then it's kind of get boring. I love how I had error. I was asking ChatGPT like 20 minutes and I found problem myself. Forgot to reset my counter. Interesting. So good at mimicking us getting dumber, just like us. Yeah. It is. For simple question is okay, but it's really shitty when you go in deeply. Yeah, so it's a very like a shallow thing, unfortunately. But can you make it deeper? Maybe just stack more layers? Maybe just stack more layers. We don't really, I think we don't even use finite differences anywhere. So if I try to compile finite differences, right? So let's actually go again from Zor. Let's go again from Zor and try to recompile this entire thing. Right, so I think all of the problems are going to be within that piece of code, region R. Okay, there we go. So G, yeah, we need to allocate G, and then alloc region architecture. So this is architecture and this architecture count. Non-void, and we have to return this entire thing. So this has to be G. That was relatively easy. And since we don't use this function in any of the demos, right, none of the demos actually like failed. Maybe we should just go ahead and try to use that in Zor, just to see if it still works. Right, we can do backprop, just replace this thing with finite differences, and the difference is going to be something like this. Yeah. So they're basically drop-in replacements of each other, right? Basically drop-in replacements. Maybe it would be even kind of cool to change the signature of finite differences to accept the epsilon at the end, so the first arguments of these both functions are the same, and finite differences has additional parameter of an epsilon to sort of emphasize that they're sort of doing similar things. Backprop tries to compute like exact gradient. Finite differences approximates that gradient. So I think that would actually make sense. Right, so and then finite differences. So this is that. And then finite differences. And in Zor, we're gonna put that epsilon at the end. And let's try to recompile. So it complains about something, semicolon, that's fine. Don't even worry about it. Okay, cool. So, and then we're gonna do the Zor, right, Zor. Does it work? It seems to be working, right? It seems to be working. That's pretty cool. But again, we don't really need to use that anywhere. It's not particularly useful because it's only approximation. So it's not useful in production. So we can do something like this. So we don't need to commit that change, only that one. So refactor and then finite diff to return nn just like nn prop. Let's push that right into the repo. Do we have any more to-dos? Right, so remove these. Okay, that's totally fine. So apart from that, that is it. Right, one of the things I would like to even do in terms of like getting rid of the activations, I think in terms of getting rid of the activation, it would be kind of cool to change nn forward to have the following signature. Right. So it accepts the region for intermediate allocations and stuff like that. Neural network, the matrix of input parameters, and returns the matrix of output parameters. And for all of the intermediate activations, it just like puts them in a region and then forgets about them. Something like that would have been useful, but I think it would be kind of difficult to refactor it like right now, right? Because there's a lot of code that expects to have this array within the neural network. It's even used for other different things. It's used quite often as an intermediate thing, and it creates a lot of like additional problem to just change all of that. So I don't think I'm gonna do it right now. One of the interesting thing I would like to do is probably refactor region itself. Because here is an interesting thing. With this specific region, we're working on a level of bytes, right? We're working on a level of bytes. But that may create an aligned situation. So essentially, okay. So in computers, I'm not really a hardware like low-level person actually. I'm a Java enterprise monkey, right? Ooga booga, write JavaScript code, public class, class static abstract. I like this kind of stuff, right? So I'm this kind of developer. So I don't really know how low-level stuff works. But on machines, there is a thing called word, right? So on 64-bit machines, a word is 64 bits, right? And essentially, you can think of memory as the sequence, not only bytes, but words, right? So, and we can maybe do something like 8. So this is a single word, right? If we think about a single dot as a byte, this is a single word, right? And you can think of memory as a sequence of words, right? As a sequence of words. And quite often, a lot of operations on the machines, right? They allow you to read a word from memory or write a word from memory, right? So, and essentially on x86 64 machines, it doesn't really matter, right? It doesn't really matter because if you try to say, okay, write a word not in here, right? In that case, it will just like replace all of the dots with this, right? But you on x86 64 machine, you can say, okay, write a word in here somewhere. And in that case, it will literally do it like this. And internally, it will actually split this entire operation into two. Right. So essentially, it will actually write half of the word here, and then another operation is going to be write half of the word in here. So from the point of view of the programmer, it doesn't really matter where you write. On x86-64, it never creates any problems. But if you do unaligned reads and writes, it just becomes generally slower. Right, it just becomes generally slow because now it needs to split this entire thing into like more atomic operations, right, into more atomic operations. On some machines, it does create problems. On some architectures, you literally cannot do unaligned read and writes. You literally cannot do them. The machine will throw an interrupt or something and your program is going to be killed by operating system. Like you can't do that. Right. Usually you don't really think about this kind of stuff, right? Because the compiler is supposed to do that for you. And in fact, this is the reason why compiler pads structures. Right. This is the reason why compiler pads structures. So essentially, if you have something like main.c type struct, right. So let's actually maybe create something like this. And let's create foo. Right, and let's create a structure that is going to have a, right, that is going to have a field. So that raises the question, what's the size of that thing? Size of foo is supposed to be equal to size of foo. So if we try to compile this entire thing, it should tell us that it is 8, which is the size of the word on that specific machine. Right. If I add uint8tb in front of this thing, what's going to be the size of this entire structure? What's going to be the size of this entire structure? Who knows the answer? Why is it not 9? Why is that 16? That's really weird, isn't it? So if I understand correctly, this low-level hackery, but I might be wrong, but if I understand correctly, this low-level hackery, it is needed so the first field is actually located on one word, and then the second field is located on a second word. So it pads the structures to minimize the amount or get rid completely of unaligned reads and writes. So is that correct? People tell me that it is correct. So I think that's the reason, but I don't want to claim anything because again, I'm not this low-level hardcore kernel hacker of Linux or something like I don't really know. I just like heard a bunch of rumors on the internet, Google that some shit, ask some shit to ChatGPT, and that's it. Like I don't claim to be sort of authority on this kind of stuff, but this is the thing that kind of makes sense to me, right? This is kind of the stuff that makes sense to me, right? And even if you just make it actually 2 bytes, it's still gonna be 16, right? Because now it just takes a little bit more. The 16 is, yeah, just takes a little bit more. If you make it 32, it's still going to be 16 because now it just takes a little bit more, right? And right, then you do 64. It's just like, yeah, it still takes this stuff because now it looks like this. So 1, 2, 3, 4. Right. And only when you introduce another thing, right? When you introduce another thing in here, it will basically bump this thing up like so, and make the structure in memory look like this, and it's going to be 24 now, right? So the size of this entire thing is going to be 24, as you can see. So that's basically how this padding works, right? If we understand correctly. Right, and it's better to keep everything like aligned by words, right? Because if we're going to be allocating structures in our region allocator, they're going to be padding so they align. But if we work on a level of single bytes, the things may end up being unaligned. Right? It would be nice if everything was kind of aligned, right? Generally. because of that, I developed over time a little bit of a trick, which I actually stole from Gia. Yeah, I think I stole it from Gia because she just submitted a pull request in one of my repos at some point, and I thought, that's a cool idea. I think I'm gonna start doing it like that from now on. Right, so essentially, instead of having like an array of characters in here, let's have an array of words. But how can we reliably take, you know, a type that is of the size of the word? Right, in C, there is a type called uint_ptr underscore t. So it's a very important type. It's a very cool type as well. So let's take a look at the definition of that type. What this type is all about. uint_ptr. ptr underscore t. Unsigned integer type capable of holding a pointer to void. It's basically the integer of the size of the pointer of that specific machine. And the size of the pointer is usually the word of that specific machine. On 64-bit machine, it's going to be 64 bits. On 32-bit machine, it's going to be 32 bits, and so on and so forth. Right. So, and essentially, when I'm allocating the region, I'm thinking in terms of not bytes, but slots, which are these kind of pointers. Right. So let's actually call them slots. And capacity is going to be the capacity of slots, not bytes. And the size is going to be capacity of slots, not bytes. So let's go ahead and just refactor everything, because now it has to be like completely different, right? Why is it going to be completely different? So imagine that you need to allocate 24 bytes. Let's put it this way. You need to allocate 24 bytes. So that means you need to fill up this area. There we go. You fill that the entire area. So that means the next allocation is going to be unaligned. So that means that you actually need to start allocating starting from here. And thinking about a region as an array of the slots, kinda, in my opinion, makes it a little bit easier. Right. So the next you may allocate, for instance, 2 bytes. Right. That will take this this amount of space, and then you actually move in here. Right. You basically leave a little bit of this kind of padding as you allocate things to actually keep all of the allocations aligned. Right. So that's basically the idea, just to keep them aligned, just to like in generally make it probably faster, right? So on x86 64, it's probably going to be faster because it will ensure that majority of reads and writes are going to be aligned, which is not going to split them into, you know, smaller, more atomic operations, right? So x86 doesn't, yeah, so this is actually a very good point. x86 doesn't care about unaligned reads, but it's better to do it anyways for portability, for sure. Yeah, exactly. That's exactly why I want to do that. Another interesting point, actually, x86 64 does care about aligned, unaligned reads and writes, but in case of CMD, right? In case of CMD, it actually can issue an interrupt if you did, like, if you actually keep the vectors in unaligned memory. At least this is something that I experienced one time when I was just like playing with CMD and stuff like that. Like I kept it in unaligned memory and I couldn't even read it. And I was just like banging my head against the wall, like what the fuck is going on, until I actually learned that it has to be aligned properly as well. Right. All right. So let's continue. Where is nn.h? So I need to, yeah. So the problem here is a little bit deeper. We use the size as the amount of bytes that is that is occupied within the region. So that means everywhere we use size, we actually have to change the semantics. So the semantic of size and capacity have changed. Right, the semantics of these things have changed, so that's why I want to rename them. Right, because in all of the places where we use them, they just basically have different meaning. I already renamed the data, I call it slots, so that also will trigger the compilation errors. So yeah, but I think from the point of view of the interface, I'm still going to accept bytes in terms of capacity and bytes in terms of size. especially in a region alloc, because this is what the users of allocators expect anyway, right? When you're trying to allocate something, you don't think in terms of words, right? You think in terms of bytes. And that's why, right, we're going to accept bytes in here, but then inside we're going to be doing conversion, right, to make sure that we allocate the proper amount of slots. Maybe it will make sense to actually call them words. I think that makes sense, right? All right, so let's do a little bit of a compiler-assisted refactoring. So we're compiling XOR, right? We're compiling XOR, and let me just go through this entire thing, right? So we have NN forward. Did I changed the NN forward signature? I didn't mean to, right? I was just like discussing what kind of changes I want to. Yeah, I didn't mean to do that. Okay, so what else do we have in here? Capacity. So this is the capacity, but in reality, we want to allocate slots. So that means we need to divide the capacity by the amount, by the size of the slot. So the size of the slot, maybe we can do slot. So let's call this maybe slot size. So this is going to be size t, slot size, and size of the slot is size of u pointer t, like this. Maybe, just maybe, I want to allocate a region up there and fill it with 0. Right, so we're going to be allocating it there and then setting it like that. Because then it is super easy to do size of R words like this. Right, so essentially, if I, for whatever reason, change the type of this thing, I won't have to change it here, right, because it will automatically change. So this gives me the capacity in bytes. So I can say, in words actually, right, capacity words. But it's not precise capacity actually. It is not in fact precise capacity, right, because if I said, all right, I want to have a capacity of something like this, right, so it has a little bit of a remainder. It has a little bit of a remainder. So, and if I take this value and divide it by the size of the word, it will give me actually 2. Right, it will give me actually 2. We can I count the amount of hashes? I can only easily count the amount of hashes if I remove these spaces. Right, then I can say how many characters we have in here. It's 18 characters. Right, if I divide 18 by 8, how much we're gonna take? Get, I'm sorry. So I divide 18 by 8, I get 2. That's precisely what happened. Right, so we lost the remainder. Right, we lost the remainder. So in reality, we need to allocate 3 slots, not 2. It has to be 3. It's very important. So one of the ways to do that, so basically rounding up. Integer round up is essentially you take this value and add it to the original thing and subtract 1. That way, you round up the integer division. You literally round up the integer division. So how does it work? Right, you want to add 8 to here. Right, so you added 8, which resulted in, actually 8 minus 1, right, it resulted in this kind of thing. Now I'm going to replace it like this. And then you divide it by 8 and you got 3. Right. In case of allocating the capacity that aligns, right, you're going to add word minus 1, which result in this kind of thing, which result in allocating 2 of them. Right, so it will cut off this remainder. So this is basically the trick that we're going to employ to round up. So this is how do you round up for integers. So essentially that means, that is very important, that this thing may allocate more than you provided in here, just to keep things aligned. It can allocate more. It reserves the right to do so. So we need to maybe document that somehow. So can capacity is in bytes, but it can allocate more just to keep things word aligned. Right. So that's very important. I think that's very important to keep in mind. And this is the amount of words we want to allocate. And here malloc, we accept malloc in bytes again. So we take capacity words and multiply it by the size of the word again. Right? Maybe it would make sense to actually do something like word size. Right, and replace it like so. So we did this entire thing to get the sufficient amount of words, and we can convert words back to bytes because we passed it to malloc, right? But this result can be bigger than this thing to keep things aligned. Does it make sense? Hopefully that makes sense. Right, and we're gonna keep track of the capacity in words. Actually, we're gonna keep track of the capacity in words, and for the words, we're gonna do it like this. And we actually accept in words in here. There we go. So that's basically how we're gonna be treating all of that. I hope I didn't make any mistakes, right? So words capacity. There we go. Cool. So let's try to recompile this entire thing. Does it fail anywhere? Capacity, it is not called capacity anymore. No capacity. Oh yeah, I renamed this entire thing to actually make sure that I update everything correctly. So it's I need to put underscore in here. So this is words. What else do we have in here? Region alloc. Okay, so that's cool. So this is size, but this is size in bytes. This is size in bytes. We need to do a similar thing. We need to convert bytes to words and also round up, right? We also need to, do we need to round up? Yeah, we do in fact need to round up. So maybe we can even copy paste this entire thing, right? So in case of region bill equal to null in here, we don't really care, but we do care about this kind of thing. So here's the word size. This thing has to be like this. Then size. Yeah, this sucks a little bit. So there's the word size, but this is a size in words, right? Maybe it makes sense to actually call it size bytes. Yeah, I think it does make sense to call it size bytes. Because the naming kind of sucks, not gonna lie. So size bytes. Maybe this capacity is also gonna be in bytes, right? Bytes. Yeah, so that's a little better. Region alloc. Size bytes, it's a word size. Size bytes plus word size minus 1 divided by word size. So this is basically size in words. We add size words and then check if it's less than capacity. If it is greater, we just increment it, right, a little bit more. And then we do the result, right? So then we do the result, and this is size words. All right, so that's basically it, hopefully. That is basically it. So size in bytes, let's go to the compilation of all of that stuff. So this is size underscore, because the, what is it called? I forgot. Semantics of these fields have changed, right? Semantics of these fields have changed. So we need to confirm that we do understand that. So this is words now. So this is size. I think I acknowledge all of that. Okay, and this is literally the reason why I renamed that field with underscore. Because we use that field outside of the library, right? Because we assumed that the size is actually the amount of bytes, but now that have changed. This size is not the amount of bytes anymore. It's the amount of words. So we need to change this thing somehow. So what I'm thinking is that maybe we are going to introduce some sort of how is it called? Some sort of a macro. Let's call it region occupied bytes. Sounds good to me. Right, and we're gonna return the size, but we're gonna multiply this entire thing by the size of the word. Words, like so. And that will give us how many bytes are occupied within that region. Right, the size and the size of the word. All right. Now, what else do we have in here? And here we can just do region occupied bytes. Do we assume that it's taken by pointer? Yeah, we do assume that it's taken by pointer, so let's actually put a pointer in here, I mean, referencing. Region, no member, size, yeah, because it's called size underscore. That is true. Cool. Is that it? Seems like it's it. Right, so we managed to successfully refactor all of that, even though it was kind of dangerous. There was one thing that I just realized, actually. What if R is null? And it can be null, actually, because region alloc assumes that it could be null. Why none of the macros in here assume that R can be null? So it's part of the interface, it's part of the agreement. I think it makes sense to actually check that. In case of the occupied bytes, we can say, okay, and then assert, right? You can't really take the amount of occupied bytes from the null region, and null region is basically falling back to the lower level allocator. So this operation should be invalid for region null. So what we have to do, we have to check that R not equal to null, and only then it makes sense to actually do this kind of stuff. So in case of region reset, it's also quite important, right? So you may try to reset. Maybe, you know what? Do you really have to crash in this specific case? Do you really have to crash? We can do something like R this, otherwise -1, I don't fucking know, right? Or maybe 0. And in this specific case, we can say if R, only then set it to 0, otherwise don't. Yeah, that's actually kind of cool. Right, so now both of the macros here kind of like assume that R can be null. And in case of null, reset just doesn't do anything, right? It's not going to do anything. And occupied bytes returns 0. So maybe that's a little bit safe. Or maybe it should crash. It kind of depends. It kind of depends on what you're trying to achieve in here. So I haven't decided. Maybe I'm going to actually make it crash at some point. Maybe I'm going to actually make it crash. Seems to be working so far. Right, so here we're using the new allocator that uses words instead of bytes. I like crashes more, to be honest, says Koikoder. You know what? I agree with you. You're a very experienced programmer, so I think I do agree with you. So let's actually crash instead. We can just do, yeah, because you may end up with a situation where you just given incorrect information, because just printing 0 is straight up incorrect. It's simply unavailable. All right, and there's literally no way for you to know whether it's literally 0 or simply unavailable. So we need to distinguish that. I think crashing is going to be better. Yeah, I agree with you. So R not equal null. And we're going to use the usual sequence trick, right? So in here, how do I organize? I'm not sure if just doing things like that is going to work, because I think this is not an expression. Oh, wait a second. It is. Assignment in C is an expression. So that should be fine. All right. Huh. All right, so that's fine. Because I'm pretty sure that you can only put expressions in here. Statements don't work in here. At least one of the things I was trying to do in here some time ago is just something like X, all right, where I would just assign X to something and then return X. This kind of stuff is not going to work because variable declaration is statement, right? This statement, and it didn't compile. Right, so you can only put expressions in here, I think. But assignment is an expression, so that should be fine. Right. If I'm not mistaken, so I don't really see that well. All right, so yeah, seems to be working. So let's go through the rest of the libraries and fix them as well, because to be fair, we didn't really change the interface, didn't we? Oh yeah, we changed the interface in the sense that now you should not access these things directly. You should use region occupied bytes. That's how we're supposed to use it now. There we go. Okay, and the same thing in here. Region occupied bytes. Cool. Very, very cool. And let me do it like that. So one of the things we probably also need to change is actually rename all of these things back to underscore, because we're done refactoring this entire thing. The only reason why I put underscores in here is because I wanted the compilation fail in all of the places where we use them, because we changed the meaning of those things. Since everything seems to be refactored, we can bring them back, right? So that will, again, break all of that stuff, but that's fine. We can just go through all of that stuff and rename them yet again. So this is another one. Should be fine. It's inside of the macro, and inside of the macro we expect this to be this. Is that it? I think that's it, right? Okay, good. Very progress. Very progress. Let's do a committee. So all the changes were made primarily inside of the library. Make region word aligned. And let's push that right into the repo. So the only thing that is left, I think, in terms of what I would like to do is get rid of the activations from here, but I think I'm gonna do that off screen, right? So essentially it's about like rearranging some stuff and everything, right? Because these things are intermediate, right? These are intermediate things and they're here for intermediate reasons. Since we're using region everywhere, we can just like temporarily allocate all of these things and we don't have to keep them within the neural network. We don't really have to keep them within the neural network, but that requires like probably like another hour or so to factor that out. So I'm probably not going to do that on stream. I'm going to do that off screen and we're going to sort of imply that. All right. So I think I've streamed for long enough today. So thank you so much for all of the subs. Thank you so much, GhostyX101 with the message hey. NazrielX, thank you so much for tier 1 with the message hello. Hope you're doing well. I'm doing fine, thank you. Lucas Nova 3, thank you so much for Twitch Prime as well. All right, so that's it for today, I guess, at least for me. Thanks everyone who's watching me right now. I really appreciate it. Have a good one, and I see you all on the next recreational programming session with Azuzin, and we're going to continue working on this thing. So yeah, thanks everyone for watching. I love you all. Mwah.